Hi, we're going to do another example using a power series to solve a differential equation. This differential equation that we have here is second order, so we know that we would need two linearly independent solutions to build the general solution for this differential equation. Before we decide what power series method to use, we would want to think about whether this differential equation has x equals 0 as an ordinary or a singular point. So one of the things we would want to think about is whether our p of x function, I have a new tablet here, so be patient with me, p of x function and our q of x function meet the criteria for x equals 0 to be an ordinary point or a singular point. Okay, so these are our p of x and q of x functions. Those are both polynomials, so they are analytic everywhere, which means that the power series method should work well. Alright, so I think we'll get rid of that writing so we have more. Okay, so we're going to start by making a guess. We'll guess kind of just the generic power series that we would always guess when we are trying to construct a power series centered at x equals 0. So there's our general form. And then we take a couple derivatives and we're going to plug into the differential equation. Alright, so remember that the power series is a big long polynomial. The first term is a constant. So when we take the derivative, the first term, the derivative of that first term will be 0. So the simplified form of my derivative series starts at n equals 1. Same thing for the second derivative. The first term on that y prime series is a constant. So when I write this series for the second derivative, we'll start at n equals 2. That's the simplified version. It would not be incorrect to start at n equals 0 or n equals 1, but the work later, oops, that should be an x. The work later will be easier if we have a simplified version. Okay, so the next thing we want to do is substitute into the differential equation. So in place of the y double prime, we'll put that series. And then we'll have minus x squared times our series for y prime. Be really careful, all the little details, the subscripts, the exponents, everything you get written down exactly perfectly because it'll mess everything up if you don't. Alright, and then the next term, so we're going to have minus 3x times our series for y. And that whole thing is equal to 0. Alright, so the next step that we would like to do here is to simplify these series. So in particular, this second series and this third series that we have, those have some simplifying that we can do. So we're going to go ahead and basically use distributive property on those two. I'm going to go ahead and write down the first one here just as is. Okay, so on this second series, I'm going to distribute through x squared, or I might choose to distribute through negative x squared. Either way, I have to remember that there's a minus sign there, so I tend to lose little details if I'm not careful. So I'm going to distribute through the negative x squared. So I'm going to put the negative out front of the coefficient, and then when I distribute the x squared to the x to the n plus 1 terms, x to the n minus 1 terms, I will end up with x to the n plus 1. So I'm taking that exponent of 2 and I'm adding that to the exponent of n minus 1. And then I'm going to do the same thing on this last series here, n equals 0 to infinity. So I'll put the negative 3 with the coefficient, and then our powers of x will be n plus 1. Okay, so the next main step is that we want to make sure that we end up all with the same powers of x. So often we change them all to x to the nth power. Here, however, two of my series are already x to the n plus 1, and then the third one is something different. So this time I'm going to convert all the series to be n plus 1 powers. So this first term that I have here, I want to convert this series so that is all powers of x to the n plus 1. Alright, so I'm going to kind of build this in pieces. I'm going to wait for a second to figure out where I'm going to start at I'm going to wait for a second to fill in these coefficients. I'm going to write what I want here. This is my goal, is to get this all in powers of x to the n plus 1. And so I need to think about what I want to start my series at so that it would be the same as the previous series. So on the series right above that, I would be starting at n equals 2, and my first power would be x to the 0. So in order to make that happen here, I need to start at n equals negative 1. And then my factors here, the first factor should be 2, so that will have to be n plus 3. My next factor should be 1, so that will have to be n plus 2. And then my c, if I look at the previous series, the subscript on that should be 2, so I'll have to have n plus 3. Oh, that's very messy. Sorry about that. I'm getting used to this new tablet. All right, so these other ones I'll copy down. Okay, so then the next goal would be to break off extra terms from the two series that have some extra terms. So this middle series starts at the highest subscript for n here, or this highest index for n at n equals 1. So these first two series, I'm sorry, not the first two series, the first one and the last series are the ones we're going to have to break some terms off from. All right, so from this first series, I will break off the n equals negative 1 term. So I would have 2 times 1, c sub 2, x to the 0. And then from the first series and the last series, they will break off the n equals 0 terms. So the n equals 0 term from the first series would have 3 times 2, c sub 3, x to the first. And the n equals 0 term from the last series will have minus 3, c sub 0, x to the first. All right, now everything that's left I can put into one big series starting at n equals 1. So this will be the n equals 1 to infinity terms from this first series. And I'm going to put some brackets here so I can pull off the coefficients and then all the other terms. So the coefficients from the first series, oh, not x. All right, so n plus 3 times n plus 2 times c sub n plus 3. That's the coefficient for the x to the n plus 1 terms from the first series. And then from the second series, I have minus n times cn, x to the n plus 1. And then from the last series, I have minus 3 cn, and all that is times x to the n plus 1. That's just collecting the coefficients for the x to the n plus 1 terms, and then the whole thing is equal to 0. Okay, so then we're going to set some coefficients equal to 0. So I have x to the 0 terms, and since the left side of the differential equation is a big polynomial and the right side of the differential equation is 0, the coefficients on the left side have to equal all 0. So for the x to the 0 terms, I have 2c2, and I wrote cn, so 2c2, and that has to equal 0. So that means c2 will be 0. And then for the c1 terms, I have 6c3 minus 3c0 equals 0. So that'll give me a relationship between c3 and c0. And then for all the other terms, I'll have this expression that's going to give me my recurrence relation. So n plus 3 times n plus 2 times c sub n plus 3 minus n times cn minus 3 times cn all equals 0. And that would be true for n greater than or equal to 1. So that all came from the series from n equals 1 to infinity. All right, let's see if I can make this screen scroll up here. Okay, so I just scrolled up the screen a little bit. All right, from this first equation, we get c2 equals 0. from the second equation, we could solve this for either C3 or C0. Usually we're going to want to solve that for the higher subscript. So if I do that, I'll get C3 equals 1/2 C0. Be careful with the fractions there. C0, C0. And then from this last expression, I can get a recurrence relation. I'm going to want to solve for C sub n plus 3. So on the left side, I'll have n plus 3 times n plus 2 times C sub n plus 3. And then I'm going to move these other two terms to the right side, and we might notice I can factor out a Cn. So I'm going to do that in the next step. All right, and then I can divide through by the n plus 3 times n plus 2. So I'll have C sub n plus 3 equals Cn times n plus 3 over n plus 3 times n plus 2. And we might notice there's some nice simplification that happens here. And that recurrence relation is for n greater than or equal to 1 from the fact that it came from that series that started at n equals 1 to infinity. That one looks like a check mark that I wrote there. Let me fix that. Okay. All right, so now our goal is to write our series. I'm going to scroll up again. All right, so I just scrolled the screen up a little bit. So now our goal is to write out the series. And so I basically just want to start listing out coefficients and then remembering from our original choice, from our original guess for y, what that means in terms of a polynomial. And then maybe we can write it in sigma notation. All right, so our first coefficient is C0, and I don't have any specific relationship about what that is, so that's just going to be C0. These two are basically going to turn into your coefficients that you end up with on your two linearly independent solutions. All right, I do have a relationship for C2 from up above. C2 is 0. Then C3 is 1/2 times C0. And then for all the other values that I get when I use this recurrence relation, when n is greater than or equal to 1, I'll get all my other coefficients from C4 on out. So for the rest of them, I'm going to use that recurrence relation for that. Okay, so for the recurrence relation, when I plug in n equals 1, I get C4 equals C1 over 3. Okay, so what we're going to end up doing here is getting all of our coefficients expressed in terms of C0 and C1. And then that'll allow us to pull apart our two parts of our solution into two linearly independent solutions. Sorry, I had some messy writing there. Okay, so on the recurrence relation, when I plug in n equals 2, I'll get C5 equals C2 over 4, but C2 was 0 from up above, so that becomes 0. C6 will be when I plug in n equals 3 to the recurrence relation, so I'll have C6 is C3 over 5, but C3 was 1/2 C0. Okay, I'm not going to simplify that and make that 1/10 C0, because if I do that, it can make it hard to see the patterns at the end. Okay, so here we go. One more, maybe a couple more coefficients here. Okay, so in my recurrence relation for C7, I'm plugging in n equals 4. So I get C7 equals C4 over 6. But C4 was C1 over 3, so I can rewrite this as 1/6 times 1/3 times C1. C8, we'll plug in n equals 5, C5 over 7, C5 was 0 though. C9 would be C6 over 8. C6 we have up above, so we can rewrite this as 1/8 times 1/5 times 1/2 C0. Okay, so you want to keep going with this until you can see a pattern in the coefficients and at least be able to predict the next few. I'm going to maybe do a couple more. Usually I do a few less, but I'm going to do just a couple more, especially since we have several that are zeroing out here. All right, so C7, C10 is C7 over 9, right? That would be when we plug in n equals 7 into our recurrence relation. Okay, so that is 1/9 times 1/6 times 1/3 C1. Okay, so I can start to see a pattern here. I think these denominators have these multiplications that are increasing by 3, so I think I could predict the next one here. Well, C11 I think should be 0, right, based on the patterns here. So let's just double check that that is true. When I put in n equals 8, I get C8 over 10, which, yep, will be 0. And then let me just make sure I can predict these next couple so that I understand what this recurrence relation is doing. All right, so I think based on my pattern here, I think C12 should be 1/11 times 1/8 times 1/5 times 1/2 times C0. So let's just double check that that works in our recurrence relation. C12 would be when I plug in n equals 9. So I'd have C9 over 11. All right, so the over 11 gives us our 1/11, and then C9 is 1/8 times 1/5 times 1/2 times C0. Yep. All right, so I think I understand this recurrence relation now and what it's generating for coefficients for me. Okay, so now I'm going to write down my solution as a big, long polynomial. So our original guess was y equals, and then our series was n equals 0 to infinity c sub n x to the n. So what that really represents is a polynomial c0 plus c1 x to the first plus c2 x squared, and so on forever. And so what we've got here, all these c's that we've got up above, are the coefficients of these corresponding powers of x in our series. All right, so based on what we found, c0 is going to be just left c0 arbitrary. C1 will be left arbitrary, C1. C2 will be 0. C3, 1/2 C0, and that will be times x cubed. C4, 1/3 C1 x to the 4th. C5 will be 0. C6 is 1/5 times 1/2 C0 x to the 6th. All right, so all I'm doing is plugging these coefficients into this big long polynomial with this c sub n times x to the nth power. So how many of these do you need to do? Well, if you want to attempt to write the series in sigma notation, you need to do enough of them so that you can then figure out what is the appropriate sigma notation. If you are not planning to write it in sigma notation, you need to write out enough terms that somebody would be able to look at it and predict the next few terms based on what you've written. If you're doing a problem on a test or something to turn in, you need to write out enough terms that your instructor can see that you knew what to do. Usually, I will say something like, give the first 3 non-zero terms in each of the linearly independent solutions. Okay, so here's my big long polynomial. We've got some terms that zero out. What we're going to do next is regroup that. We're going to regroup that. So I've got a bunch of terms with C0 as the coefficient. So I'm going to regroup those. So I have 1 plus 1/2 x cubed plus 1/5 times 1/2 x to the 6th plus 1/8 times 1/5 times 1/2 x to the 9th plus dot dot dot. Remember, this goes on forever, so that's one of my series solutions. And then C1, all the stuff times that. So I've got x plus 1/3 x to the 4th plus 1 over 6 times 3, 6 times 3, x to the 7th, plus, let's see, I'm going to write one more, even though I didn't have it up above. I have all those coefficients up at the top here, so we can think about what those would have been. 9 times 6 times 3 x to the 10th plus dot dot dot. Okay, so for each of these series, I have 4 non-zero terms in each of these series. So the instructions in the book sometimes say a specific number of non-zero terms in each series. All right, I could stop there. I should probably write y equals. I probably could stop there if I wanted, as long as you have at least the number of non-zero terms in your series that you're being asked to produce, and or that the reader could pick that up and see what the pattern is enough to predict the next term in each series. So that could be how you leave your answer. Okay, so we might see that we can rewrite these series, particularly the second one actually, in sigma notation pretty easily. So I'm going to leave the first one as is for right now. Okay, and then this second one, the powers of x are increasing by 1 each time, and the denominators are all products of multiples of 3. So if I start this one at n equals 0 to infinity, and I let my denominator be 3 to the n times n factorial, and I let my power be x to the 3n plus 1, I think that will generate all the terms correctly. Let's double check. When I put in n equals 0, I get 1 times x to the first. So that's okay. That's what I wanted. And then when I put in n equals 1, I get 1 over 3 times x to the fourth. So that's good. When I put in n equals 2, I get 3 squared, that's 9 times 2, 18, all right, and x to the 7th, and n equals 3. I'll get 3 cubed times 3 factorial, which is the same thing here. If you write this all as products of 3, this would be 3 times 3, 3 times 2, 3 times 1. So that's the same thing as 3 squared times 3 factorial, and x to the 10th, right? So this is another way that you could write your answer. You could write your other series also in sigma notation if you want. I'm probably not going to try to. The powers of x are pretty easy to do, but you have to fiddle a little bit with that denominator to get that in a nice clean form. It's got these factors that are increasing by 3 each time, but it doesn't factor quite so nicely like this second series does. So I'm going to go ahead and leave it like that. The other thing that we could do is check interval of convergence on each of these. Both of these have an infinite interval of convergence. You could use ratio test to show that. So you would want to just check that, and both of these are infinite interval of convergence, which is good. So we've got a nice series solution to our original differential equation.